Well, if Renata can explain what I'm doing here, then I'm certainly lost for words too about that. But I'm not on the CIG executive committee or steering committee. I did help write the proposal for the renewal of CIG, which was successful last year. Louise Kellogg is the chair or the director of CIG. She couldn't be here for personal reasons, and she asked me to represent CIG for that, which I'm happy to do. I'm feeling like I'm wearing all sorts of different hats, and none of them fit too well. I'm also on the Compress Advisory Council. At least I came once, and I'm not sure I'm going to be invited back again because I actually decided to give advice this time, and that's, you have no choice. All right. So I want to talk a little bit about what CIG stands for. The title is, it's a bit of an unfortunate acronym. The first time I heard it, I thought there was somebody wanting to smoke cigarettes or didn't feel too well about it. But it's the Computational Infrastructure for Geodynamics. It started about 5 years ago as an effort to essentially provide what you're doing here, provide a community of people who can benefit from combined computational development, resource allocation, tutorials, sharing experiences and the like. And then specifically for geodynamics, meaning large-scale plate tectonics, earthquake cycles, magma dynamics, and the like. So Luis provided most of the slides for this. A little bit of history, 2004, the first CIG phase was started at Caltech under the leadership of Mike Gurnes. Cooperative agreement from NSF. Budget was roughly $1.5 million per year at that time. Moved to UC Davis last year, or this year, effective just recently with Luis taking over. Again, a new cooperative agreement for 5 years. It's governed by the members. We have about 45 institutions that participate. There's a simple voting system for the executive committee and the science steering committee. Then there's a number of volunteer committees, working groups that work on different aspects and help guide the staff that are working on the variety of the problems. Everything you can find on geodynamics.org in terms of the governance, the software, and the like. This is a NSF-geared slide in terms of goals and operations, so the language is a bit loftier than I would have put it together. But really it is to try to see how you can make complex problems solvable by working together across disciplines, across time scales, across length scales. And those are some challenging. If you look at basic Earth dynamics, you're looking at very long-term mantle convection, which takes place over the age of the planet, so 4.5 billion years. You're also looking at earthquake cycles, which take place over 10, 15 seconds. You're looking at magma dynamics, which takes place over crystal scales. You're looking at plate tectonics that takes place over 10,000 kilometers, and they're all interacting with each other. So you want to somehow find a way of integrating, going across those large dimensional jumps. These CIG's component of that is to try to use best practices out of computational science and apply that to the Earth dynamics code by using and optimizing existing codes and developing new ones, maintaining that and developing a community through workshops and training. At UC Davis, the location allows for interaction, similarly as what you would find at any big university like University of Minnesota. You do have big departments that allow you to work with them. You have the basic infrastructure for high-performance computing and networking. Louise also is director of the Keck Caves, similar virtual visualization environment. She's imaged here with Magali Billen working on a subduction zone model. And the proximity to national labs is also beneficial. The current budget is about $1.6 million per year for 5 years. It's a very simple breakdown. 80% goes to staff, principally the people who develop the codes, some management, secretarial staff. 20% goes to community activities, including workshops for which participants are invited and the travel is being paid for, and some short courses that are offered at a variety of larger meetings. The principal code support takes place through a staff of software engineers. That team is now in transition. One moved from Caltech to Davis, and there's a number of openings for that. And a technical writer to provide the documentation for the software. There's a staggered support level, depending on whether code is really maintained, developed in-house at level 1 support, distribution of existing code with documentation and bug releases and improvements towards new platforms without fundamental development of the code, and then some distribution of codes as they are. I've tried to minimize the number of names that are probably not that meaningful for this community, but there's just 2 codes I would like to highlight because they're mantle convection code. Sitcom-S is a spherical mantle convection code, does large-scale plate tectonics, essentially. And then Conman, which is the level 2, it's got a bit of an unfortunate name, perhaps. It stands for convection in the mantle. It's a very old code developed by Scott King, has gone through a number of generations of rewrite, but is maintained at a level 2 for within CIG. There are a number of working groups that work on different parts of the problem and try to engage the community, steer the scientific development, try to get the attention of the software engineers to work with high priority on their problems. And those are based essentially on some of the more traditional disciplines and the end of timescales. And there's one thing that I would like to point out, principally the long-term tectonics and the short-term tectonics. This is not a natural division, but it's a practical division to look at how long does it take to build up a mountain and erode it down to what's happening to earthquakes. Well, all of them are related, and so what you really would like to do is start combining or at least integrating those two. Activities come from the community. Every member is invited to propose things. The executive committee, together with the science steering committee, evaluates those requests and sets time. Eventually, everything is approved by the executive committee. In terms of building the community, we go through a relatively straightforward but rather active scheme of doing workshops and short courses. We go through the communities that benefit from this, which is EarthScope, which is a large seismological observational community, IRIS, which is the database management, SCEC with Southern California Earthquake Center, CIDER is the collaborative infrastructure for deep earth research, which essentially a number of you have been to, in this audience have been to those sessions, either as teachers or as participants. And that also provides to combine or create a community of people to teach each other about integrated earth discipline. One nice thing about CIG is that because it represents a community, it's relatively easy to write proposals to TeraGrid, for example, and to get an allocation. And it makes it easier for individual users to get access to it instead, rather than writing fundamentally your own proposals to TeraGrid. Just one example of some of the ideas. This is a bit of a busy picture out of the proposal that we provided about how you can combine seismology with geodynamics, with magma dynamics, and then provide the visualization of that. I would like to highlight for this community one important, and if there's one thing you want to get out of my presentation, it's this. This is the model of the Earth, and this is the relative size of the Earth's core, based on seismological observations. Gutenberg discovered that about 100 years ago. Now, we are Earth scientists, and we're very, very sensitive to the size of the core. And so I've now seen multiple presentations already this morning where, admittedly in cartoons, but there are core sizes that go from that of Mercury, which is much bigger than that of the Earth in relative size, to something that's much smaller. And so if you are preparing for your proposal and this goes to an Earth science community, take a look at what the real size of the Earth's core is. You, not pointing fingers. Okay, so that was my attempt at a comic interlude. So sorry it failed, and horribly upset and sensitive people in the audience. But anyways, science questions that we like to do. In terms of I've kind of addressed these large-scale things, really looking at global scale perspective about how did the Earth evolve over a long time. What's happening at the plate boundaries? That's kind of where all the action is. That's where we have the magmatism. That's where we have the earthquakes. And how do we, if we have these models, integrate them with the observations? We would like to make models that actually make sense compared to the observations. And there's always the approach to do lots of models and pick the one that looks okay. You can also start looking at the inversions for that, developing adjoint methods and the like. That's very complicated, but it's part of the process that we like to approach. Some methodologies that we've started using with moderate success to good success, particularly adaptive mesh refinement is probably an essential tool to really make use of the fact that where the action is, you want to have the high resolution, and so you can. You know, this is this is this is this is a this is a very small part of the Earth, very largely extended. So it's one of those things that goes to infinity and then around again. But, this is a model. It's not the real Earth. But when we apply for funding, we make it look good. If you have at places where you have downwellings, you get a lot of action, a lot of strong boundary layers, temperature, in velocity, and stress. Since the minerals deform by non-Newtonian deformation, you need to resolve the stress gradients as well. And so the best way to do that, and this is not represented on this image, but there's actually a representation of here of a very fine grid that evolves with the solution itself. Those methods are hard, particularly in 3D, but there's now some relatively good base codes that have been developed that can be used by application users. There's also multi-physics coupling. If you look at a subduction zone, this happens to be Nicaragua subduction zone where the temperature is represented by contour lines. The complicated pattern on top of that is the predicted fluid flow that comes from there. The fluid flow takes place over grain scales. The subduction zone takes place over 1,000-kilometer type scale. And those are very hard to couple with each other, particularly if the fluids and the melts have an influence on the rheology and the buoyancy, and therefore influence large-scale flow, which they do. It's just very hard to resolve that. But that's some of the things that we're working on. I think I left all the titles of the codes out of here, except one. Basically, we're trying to progress based on the last 5 years of experience to improve the usability, the accuracy. We're developing benchmarks for a variety of things, and we're trying to integrate these methods. So in terms of CIG is an entity by itself. It's funded for 5 years within its current contract. It can't really promise to do anything. But there might be a possibility to say, let's expand what CIG is doing to help out with what Compress is doing, either by writing an additional grant into the collaborative agreement, or just thinking about collaboration on a no-cost basis, or just to share best practices and help you continue your development of your community. So that's really a lot of potential, and there's no need for collaboration, but I think we have something to share between these communities. Certainly in terms of the infrastructure of dissemination and distributing of codes, which are documented, bug tested, things like that, the training and the workshops, and the access to computational resources. Those three seem to be segueing in pretty naturally with what I've been hearing about what you want to develop. So my question to you, or my questions to you really, is what are you looking for in this? Renat in the introduction basically mentioned all of the people, access to core cycle, cyber infrastructure, data storage, etc. But at what scale is that? Is this enormous? Is this way beyond what CIG is doing? Is this smaller? Is the structure that we have, which got grown out of its own, is that attractive to your community? Is that something that you say, well, help grow and we'll grow into that? Or do you just want to borrow the ideas? Do you just want to extend VLab at MSI as the basic vehicle for that? Those are all on the table, of course, and I'd be happy to talk with you more about that in the next day and a half, or next day.
You probably are going to get more questions than anybody else so far. Questions?
Yes.
Yeah.
Thank you. A specific question. When you are financing the software development, is it in the form of, say, postdoc positions affiliated with specific university groups, or like software engineers affiliated with CIG better?
Okay, the way we develop the codes and maintain the codes is by dedicated software engineers that are on location with the director. So they used to be at Caltech, and now they're moving to UC Davis. So it's not postdocs at institutions, it's really people at that institution. So there's no travel money to work with these people on site, it's all remote collaboration. The community interaction is through the workshops, etc.
What's the number of participants?
Well, it's 45 institutions. We're probably talking about a community. The renewal workshop that was held had about 120